fact, we will call it preconditioning matrix. And instead of just using the diagonal, we can use all the coefficients of the matrix so that maybe I can rotate the ellipse in the opposite direction. I can rescale the axis, and at the end, this matrix will have as an effect to bring this function, which is complex to optimize, to this function. It's like I will be doing gradient descent on an isotropic function by using this preconditioning, then using this function if I'm not using this preconditioning. So this m is only to make the work easier. But m has the dimension of a number of parameters times the number of parameters. And in deep learning, number of parameters of a model is around 1 million parameters. And many algorithms in the optimization community, in fact, they are computing another matrix with the same dimension. So they will fill 1 million by 1 million values in this matrix, and they will take the inverse of this matrix. So in memory, it's really big to start a matrix of 1 million by 1 million in memory. But moreover, most optimizers in the optimization community will ask to do the inverse of it, because usually I want to divide these values by a scaling factor, and I must inverse this. And so deep learning will not be able to use very good optimizer that will rely on the full preconditioning matrix because of the size of this matrix and also the inverse operation that many algorithms required. The inverse of a diagonal matrix is just the inverse of the elements in the diagonal. It's much easier to compute. And this is what we will use to define a better optimizer. So now we have our preconditioned gradient descent algorithm here. But I still need to specify what will be the numerical values that I want to use in M. And M is diagonal. So one first optimization algorithm that is used a lot in the community is RMS-prop. The gradient here will provide me, the -1 times the gradient will provide me a descent direction. I'm sure that if I move in the direction of minus the gradient, the loss will decrease. Maybe I need to move very, very slowly because the function is highly nonlinear, but it exists at eta sufficiently small that will guarantee me that the loss will decrease if I move in the direction of the gradient. Now I'm multiplying this gradient by a matrix, and maybe I don't have a descent direction anymore. Maybe I will lose this property that the gradient is a descent direction. So to be sure that I'm not reversing the descent direction, I must be sure that M is positive definite. And to be sure that M is positive definite, I just need to ensure that all my values are positive. They don't have different sign. And I will be sure to preserve the property that I have a descent direction. So this diagonal must be positive. And one simple way to rescale the parameters is to divide by the square of the gradient. So this equation must be interpreted by component. So I will maintain an auxiliary variable Vt, and I will update Vt by the beta. Beta is a hyperparameter, times the old value of V at times t minus 1, plus 1 minus beta, that I will do the multiplication with the square of the gradient, but for the component relative to one parameter. And here, to update my parameters, it will be the old version of my parameters plus 1 over the square root of this value, which will be positive. And then I multiply this by the gradient. And it will scale down in some way the axis so that the condition number is better by using this simple technique. And so RMS-prop usually works better than just vanilla gradient descent. in terms of optimization. It's faster to minimize the loss function on the training set.